Running time of the algorithm. Let U equals to maxima of Uij, where the maxima is taken from I in B and J in A, and let delta equals to n times U to the n. Lemma 5.12 at the termination of a phase, the prices of goods in the newly tight set must be rational numbers with the denominator less than equals to delta. Prove let S be the newly tight set and consider the equality subgraph induced on the bipartition S gamma of S. Assume without loss of generality that this graph is connected. Otherwise, we prove the lemma for each connected component of this graph. Let J and S. Pick a subgraph in which J can reach all other vertices J prime in S. Clearly, at most 2 times set of S is less than equals to 2n edges suffice. If J reaches J prime with a path of length 2L, then Pj prime equals to A times Pj over B, where A and B are products of L utility parameters, Uik's each. Since alternate edges of this path contribute to A and B, we can partition the Uik's in this subgraph into 2 sets such that A and B use Uik's from distinct sets. These considerations lead easily to showing that M of S equals to Pj times C over D, where C is less than equals to delta. Now Pj equals to M of gamma of S times D over C, hence proving the lemma. Lemma 5.13. Consider 2 phases P and P prime not necessarily consecutive, such that the good J lies in the newly tight sets at the end of P as well as P prime. Then the increase in the prices of J going from P to P prime is greater than equals to 1 over delta squared. Prove let the prices of J at the end of P and P prime be P over Q and R over S respectively. Clearly R over S greater than P over Q. By lemma 5.12, Q is less than equals to delta and R is less than equals to delta. Therefore, the increase in price of J, R over S minus P over Q is greater than equals to 1 over delta squared. Within the phase, we will call each occurrence of events 1 and 2 an iteration. Lemma 5.14. The total number of iterations in a phase is bounded by n. Proof. After an iteration due to event 2, at least one new good must move into the active subgraph, since there is at least one good in the active subgraph at the start of a phase. The total number of iterations in a phase due to event 2 is at most n-1. Finally, the last iteration in each phase is due to event 1. The lemma follows. Lemma 5.15. If F and F star are respectively a feasible and a balanced flow in N of P such that gamma I of P F star equals to gamma I of PF minus delta for some I in B and delta greater than 0, then the square of the norm of gamma of PF star is less than equals to the square of norm of gamma of PF minus delta square. Proof. Suppose we start with F and get a new flow F prime by decreasing the surplus of I by delta and increasing the surpluses of some other buyers in the process. We show that this already decreases the L2 norm of the surplus vector by delta square, and so the lemma follows. Consider the flow F star minus F. Decompose this flow into flow paths and circulations. Among these, augment F with only those that go through the edge IT to get F prime. These are either paths that go from S to I to T or circulations that go from I to T to some I, L, and back to I. Then gamma I of F prime equals to gamma I of F star equals to gamma I of F minus delta, and for a set of vertices I1, I2, I3 until Ik, we have gamma I L of F prime equals to gamma I L of F plus delta L, such that delta 1, delta 2, delta 3 until delta K, all of them are greater than 0, and the summations of delta L summing with index L starting from 1 to k is less than or equals to delta. Moreover, for all L, there is a path from I to IL in R of Pf star. Since F star is balanced and satisfies property 1, gamma I of F prime equals to gamma I of F star greater than or equals to gamma IL of F star greater than or equals to gamma IL of F prime. By lemma 5.16, the square of the norm of gamma of Pf prime is less than or equals to the square of the norm of gamma of Pf minus delta squared, and since F star is a balanced flow in N of P, the square of the gamma of the square of the norm of gamma of Pf star is less than or equals to the square of the norm of gamma of Pf prime. Lemma 5.16. If A is greater than or equals to B, I greater than or equals to 0, I equals to 1, 2, 3 until n, and the delta, which is greater than or equals to the summations of delta j, summing with index j starting from 1 to n, where delta j, which is greater than or equals to 0 for all those j starting from 1 to 3 until n. Then the square of the norm of A, B1, B2, B3 until Bn is less than or equals to the square of the norm of A plus delta, B1 minus delta 1, B2 minus delta 2, and so on until Bn minus delta n. Such a square minus delta square. Proof. A plus delta square plus the summations of Bi minus delta I square, summing for all those I starting from 1 to n, minus A squared, minus the summations of Bi squared, summing for all those I starting from 1 to n, is greater than or equals to delta squared plus 2a times delta minus the summations of delta I summing with index I starting from 1 to n, which is greater than or equals to delta squared. Let n0 denote the network at the beginning of a phase, assuming that the phase consists of k iterations, and that nt denotes the network at the end of iteration t. Let ft be a balanced flow in nt for all those 0 less than or equals to t less than or equals to k. Lemma 5.17. Ft is the feasible flow in n t plus 1 for 0 less than or equals to t less than k. Proof. The lemma follows from the fact that each of the two actions, raising the prices of goods in J or adding an edge as required in event 2, can only lead to a network that supports an augmented max flow. Corollary 5.18. The norm of gamma of nt is monotonically decreasing with t. Let delta t denote the minimum surplus of a buyer in the active subgraph in network nt for 0 less than or equals to t less than k. Clearly, delta 0 equals to delta. Lemma 5.19. If delta t minus 1 minus delta t greater than 0, then there exists an I in H, such that gamma I of pt minus 1 minus gamma I of pt is greater than or equals to delta t minus 1 minus delta t. Proof. Consider the residual network R of ptf corresponding to the balanced flow computed at the end of iteration t. By definition of ht, every vertex v in ht remove ht minus 1 can reach a vertex I in ht minus 1 in R of ptf, and therefore by theorem 5.5, gamma v of pt is greater than or equals to gamma I of pt. This means that minimum surplus delta t is achieved by a vertex I in ht minus 1. Hence, the surplus of vertex I is decreased by at least delta t minus 1 minus delta t during iteration t. Lemma 5.20. If delta t plus 1 less than delta t, then the square of the norm of gamma of nt minus the square of the norm of gamma of nt plus 1 is greater than or equals to the square of delta t minus delta t plus 1 for 0 less than equals to t less than k. Proof by lemma 5.19. If delta t plus 1 less than delta t, then there is a wire I whose subplus drops by delta t minus delta t plus 1 in going from ft to ft plus 1. By lemmas 5.15 and 5.17, we get the desired conclusion. Lemma 5.21. In a phase, the square of the L2 norm of the subplus factor drops by a factor of 1 minus 1 over n squared. Proof. We will first prove that the square root of gamma of n0 minus the square of the norm of gamma of nk is greater than or equals to delta square over n. Observe that the left-hand side can be written as a telescoping sum in which each term is of the form the square root of gamma of nt minus the square root of the norm of gamma of nt plus 1. By corollary 5.18, each of these terms is positive. Consider only those terms in which the difference delta t minus delta t plus 1 is greater than 0. Their sum is minimized when all these differences are equal. Now using lemma 5.20 and the fact that delta 0 equals to delta and delta k equals to 0, we get that the square root of the norm of gamma of n0 minus the square of the norm of gamma of nk is greater than or equals to delta square over k. By lemma 5.14, k is less than or equals to n given the desired inequality. The above stated inequality and the fact that the square of the norm of gamma of n0 less than or equals to n times delta square gives us the square of the norm of gamma of nk less than or equals to the square of the norm of gamma of n0 times 1 minus 1 over n squared. The lemma follows. Theorem 5.22. The algorithm finds equilibrium prices and allocations for linear utility functions in a Fisher's model using big O of n fourth n to the fourth times log n plus n log u plus log n max flow computations. Proof by lemma 5.21. The square of the subplus factor drops by a factor of half after big O of n squared phases. At the start of the algorithm, the square of the subplus factor is at most m squared. Once its value drops below 1 over delta to the fourth, the algorithm achieves equilibrium prices. This follows from lemma 5.12 and 5.13. Therefore, the number of phases is big O of n squared times log of delta to the fourth times m squared, which is equals to big O of n squared times log n plus n log u plus log m. By lemma 5.14, each phase consists of n iterations, and by lemma 5.11, each iteration requires n max flow computations. The theorem follows.